know about the supervised learning, because K nearest neighbor is a supervised learning algorithm. And within 2-3 minutes, we'll come to the algorithm, but just want to recap the things which we already have discussed. So supervised learning means,
Sir,
so we have,
sir, one second. Sir, you sorry to interrupt. You can maybe do it in the presenter mode. I mean, you can slide show it.
yes, so, sorry.
Yes, thank you.
So supervised learning, we already have the training data and the labels, and the objective of the classifier is to learn the mapping between the training data and the labels. So when we try to develop a machine learning model in supervised setting, so the first objective is to understand what is the problem, and given the data and the problem, the features which we extract generally depend upon the target problem. So for example, if we have a data of different size, shape and color, and the objective is to classify new sample based on the shape, so the features will be differently important. And if we are the objective is to develop a classifier for distinguishing between the colors, in that case the different features will be important. So given the data, based on the target problem, the different features may be important and not important depending upon the problem. So for this example, if we want to classify a new sample based on the shape, in that case, color is not important. But in case if you want to develop a classifier which for the color, then the shape is not important. Okay, so the steps to apply machine learning model is to first identify the problem, if it is a classification problem, regression problem, clustering problem, or any other problem. So based on the problem, we first collect the data and pre-process the data and choose the appropriate machine learning algorithm for the purpose which we are trying to develop a machine learning model, and then we evaluate. So the objective of these process is to extract the features in a way that represent a feature vector, and feature extraction part is the most important component of developing an efficient machine learning model. So for this example, the objective of machine learning model is to convert the raw data into these feature vectors. For this example, let's say we have n attributes of the features, and the class attribute is given to us. And from this training data, we want to learn some pattern and given a new testing example. So for this example, if we are given these values, we want to classify this into a predefined set of categories like A and B. So for this purpose, first step is to understand that which features are important and what is the properties of the features. So in general, given these, like for example, I've taken two attributes, A1 and A2. If you will carefully see these values, A1 and A2, so one feature is important, one feature is not important. So given this new training sample, sorry, testing sample, if 42 is the value of A1 and 52 is the value for A2, so based on the training data, we should be able to understand that A1 or A2, which feature is important. So feature A1, if you'll carefully see in the training data, that if you'll carefully see, then you'll notice that the values of A1 is higher for A1 for class A and very low values for class B. So it means that A1 is a feature which is very distinguishing. And if we see a higher value in the testing example, for example, 42, so 42, it means that A1 is important and it is giving some information that this new feature, this value of A1, 42 is suggesting that this sample should belong to class A. And for example, A2, the values are not distinguishing, so A2 is not a very important feature. So feature extraction part is to develop a feature vector in which all the features are relevant, important, which is problem specific, and there should not be any correlation and redundancy among the features. So this is the most important part that we do in the feature extraction and processing part. And all the features which we have for the training of the model should be distinguishing. And distinguishing means for A1, this feature is distinguishing because it is conveying that, okay, the value, high value is and conveying that this sample should belong to class A, and so on. So this is the thing which I wanted to recap. I'm sure this you already learned in different lectures. So once we have this kind of feature vector with us and labeled with us, we can use different machine learning algorithms. And the nature of different algorithms is different. For example, you will be learning linear regression, logistic regression, neural network, support vector machines. All these are the models, are the algorithms which are based on learning some weights and the parameters and separating lines and hyperplanes and so on. So those are the algorithms which are basically parametric method. And the learning algorithm which we are going to learn today is k-nearest neighbor is a supervised machine learning algorithm. At the same time, it is a non-parametric method. K-nearest neighbor algorithm is very simple algorithm, and it is very easy to implement. We'll learn how we can do implement and work on k-nearest neighbor algorithm. But the most important thing about k-nearest neighbor is that it is a non-parametric method, in which it means that in logistic regression, for example, we give the training data, we try to learn a equation of a line which separates the training samples, and we learn the parameters, weights, and so on. But in k-nearest neighbor, we don't generally have those kind of things. So we just give the train based on the training data. We directly, try to classify new sample. So logistic regression is basically used to train the models based on the underlying principles of the data, in which we learn the weights deriving from the data. But in k-nearest neighbor, we don't learn the parameters. Even in this, we directly use the data for the classification. So the value of k in k-nearest neighbor is not a parameter. It is just a tuning parameter that we give, like 2 nearest neighbor, 3 nearest neighbor, and so on. But it is not a parameter which we learn from the data. So that is an important thing that we have to keep in mind. And in k-nearest neighbor, there is no explicit training phase. We directly use the training data at the time of testing data. Yes, so that is why it is also called as lazy learner algorithm and rote learning algorithm, in which we generally memorize the whole training data in one memory, and then when we have testing data, we use the whole training data for classification. So we'll see how we'll do it, but this is the basics of about the k-nearest neighbor algorithm. So the idea about the k-nearest neighbor, it is also called as instance-based learning, and in which we try to find out the examples which are similar or close to the testing sample, and we identify those samples from the training example, and we see the what is the label of those closest samples, and we give the labels of those similar or closest samples. So the idea is to find out the similar training examples, and we use those labels for training samples for classification. And for this, first thing is whenever we have a new sample, we try to find out the similar examples. The question is how many similar examples, and how we find out the similarity between the samples. So these two important questions that we should know for applying the k-nearest neighbor, and that we'll learn in the further discussions. Okay, so whenever we have this training data and testing samples, we try to find out the closest samples, and we use them in those informations. And one of the important thing is for k-nearest neighbor, the input data can be in any form, like numerical, it can be categorical, and output form is categorical values. Generally, for the classification, we have categorical values in which we which we can use for based on the majority voting. We can classify the new sample, and if we can also use k-nearest neighbor for the regression, in which we find out the closest samples, and the output can be based on the averaging of the similar samples. So the k-nearest neighbor can also be used for both classification and regression problems. So one nearest neighbor is an simplest form of k-nearest neighbor algorithm, in which all the training samples are given to us, and the idea is to find out the label of the new sample based on what is the closest example. For this example, you can see that this new label, which is in new sample, which is in black, and the closest sample is this red one. So since it is the closest sample is having a red as a label, so we'll label next testing sample as a red. So, and the algorithm is the k-nearest neighbor algorithm formally can be described as follows, in which in the training samples, all the training phase, all the training examples are, yes,
No, your voice had gone in between, so that's
sorry.
now it is now.
Am I
it is-
audible now?
Yes, yes, yes.
Okay, so in k-nearest neighbor classification algorithm, in the training phase, we are given all the training example which we save in the memory, and at the prediction time, we firstly we should know that what is the value of k, because that we firstly know that what is the value of k, and we try to find out. We'll also talk about how to find out the best value for k. So for k nearest neighbor, we key value of k is given in priori, and this is the data set, which is a training data set. And when we want to classify a new sample for each test sample, which may be denoted as z, and x dash and y dash. X dash is the feature vector for the testing sample, and y dash is the label if it is given to us, so we can see what is the predicted value of the algorithm and what is the actual given label to that sample. So first step is to find out the distance of new sample Z and every example of the corpus. And then we calculate the distance for all the samples, and then we find out the k closest training examples, which is close to Z. And then based on the majority voting of all those k samples, how many of them are having a particular class. So majority class will be the class of the new sample. So this is the formal definition and the algorithm of the k nearest neighbor, in which the most important component of the algorithm is how we can find out the distance between a new sample and all the training samples. And we'll also talk about how we can, what are the issues which we'll face in k nearest neighbor, that what is the best value for k that we should keep, how to find out the distance between different samples, and what will happen if the training corpus becomes very large. Because this algorithm is very lazy in the training part, which don't take much time for the training, but at the testing time, if the samples are very large and feature vector size is also large, then it becomes very inefficient algorithm. So this is another example for nearest neighbor classifier, in which plus and minus, these two kinds of samples are stored in the training corpus, and new sample, which is denoted with red. For this example, there are three nearest neighbor we are talking about. Then based on these three, we can see that all these three are basically plus. So based on the majority out of three, how many are plus, how many samples are in the plus category. So based on the majority, we can classify, or we can label the new sample as plus. Okay, so that is an example which we can use to classify. And in k nearest neighbor, there is one concept like Voronoi diagram, which we can draw for one nearest neighbor algorithm. So one nearest neighbor means this Voronoi diagram is basically a graphical representation uh, of one nearest neighbor algorithm, in which each region, which you can see in the left hand side, that each region in the Voronoi diagram corresponds to the decision boundary for that class. So for this example, if we draw the one nearest neighbor algorithm using the Voronoi diagram, which is basically a geometric visualization that partitions a space on the nearest point. So for any region, if you will talk about this region, so any sample which falls into this region will be the label for this sample which is present in this. So that is purple region, for example. So this is a graphical representation of decision boundary for one nearest neighbor, which we can visualize. And in the right hand side also, which you can see that this is also a Voronoi diagram for this. So based on this visualization, we can use that Voronoi diagram for one nearest neighbor, and we can immediately classify a new sample based on the decision boundary of that. So since we know that k-nearest neighbor classifier, a new sample will be classified based on the distance between the new sample and the training samples. How we can calculate the distance? The most popular method in k-nearest neighbor to calculate or compute the distance is Euclidean distance, in which given a new sample and the samples of the training corpus, we calculate the distance using the Euclidean distance, which is very straightforward method, which is to just see the difference between each feature value and the square, and then do the weighted average and then square root of this. The Euclidean distance and Manhattan distance we can also use, and Q norm form distance can be used. There are other methods for distance metric also, but the Euclidean distance is mostly popular. We can also experiment for all data the different distance metrics, so that is also possible. But in k-nearest neighbor, the most popular one is Euclidean distance. So it's straightforward to compute the Euclidean distance for a new sample with all the training samples, and we see that what is the best the closest samples, and based on those we can classify the label or to classify the new sample. And this in this diagram we can observe that the distance metric which we use for the classification is very important. And if we try to change the distance metric, you can see that the decision boundaries are also changing a lot. So with this, this field metric is an important criteria when we are using a k-nearest neighbor for our problems. So we can empirically decide that what is the best distance metric we should use for our data. So yes, so that is the important thing which we should take care when we try to develop a k-nearest neighbor for our examples. And in this example, if you'll notice, this is an illustration for k-nearest neighbor. And if we focus on this, when k is equals to 3, so if this is a new sample, let's say, and all these three are blue class 1, and for this, we can see that all these samples which are coming for this training sample, for this sample is class 2. But if you carefully see that it is automatically trying to find out the decision boundary. We are not learning any decision boundary, but if you'll carefully see this diagram, you can see that the for k is equal to 3, if you draw any decision boundary or any, you will take any example, the samples which are far from this boundary will always be easy to detect. And for those which are far from here, all those samples are easy to classify. The problem will be when we basically have very close to the boundary. So somehow, if the data is linearly separable, the k-nearest neighbor can automatically learn those patterns and then it will give the problem when we are close to the boundary, which generally happens in the all other algorithms also. So k-nearest neighbor algorithm is very good algorithm in the sense that it can, without giving any parameters, it automatically try to find out the boundaries, and on the boundaries it will give some problems. But apart from that, if you try to develop any for k, let's say k, for k is equal to 5, any samples you will try to classify, there will not be any problem. So for this example, you will see that the samples which is near to the boundary, yellow one is the test data. So in that case, there might be some problems, but any other case, so for example, let's say for this case equal to 3, if you have some sample here, there will not be any problem, or any other samples. So with this example, I wanted to explain that k-nearest neighbor is an algorithm which has very nonlinear boundary, decent boundaries, but it also works nicely for the training data where we can linearly separate, which is linearly separable. It automatically learns the decent boundaries, and the boundary where there might be some problem, but we can choose the value of k and decide that what is the best value for that data, and it can perform good in that sense also. So this is the k-nearest neighbor algorithm in which we given all the samples, training samples, and if we have a new sample we want to classify, we have to decide the value of k, the parameter, and then the distance metric, and then we, based on the majority voting, we can classify the samples. But now we'll discuss the problems which may face and the things which we should keep in mind while using k-nearest neighbor. First thing is parameter selection. In the parameter selection, the value of k is very important. The performance significantly depend on k, specifically when there is no there is a lot of noise in the data. So okay. So when there is the value of k, because we'll see in detail that how to decide the value of k. The value of k is when we have a small value of k, so noise will be a problem. And when we increase the value of k, we can tackle some noise, but uh, since k-nearest neighbor is an algorithm in which all the features are taken equally. The Euclidean distance is a metric which takes all the features equally, and if there is any noise, it will deteriorate the performance. So presence of the noise is very important. We have to use the feature selection and reduction method. We have to decide the value of k very carefully, and then we have to do the scaling as well, because scaling is also important in the sense that if we have a feature, like for example, one feature is having the values in the range of 1 to 100, and another feature is having in the values in the range of 1 to 10 or 0 to 1. So the feature which is having higher range will dominate or will contribute more in when we'll try to compute the Euclidean distance, because Euclidean distance will take all the features equally, and the features which will have higher range values will dominate. So it is important that we scale all the features and bring every feature in one range or with a standard deviation, equal standard deviation. And also it is important to take care of the dimensionality, because when there will be large number of features and a large number of samples, the performance of the algorithm will become very slow, because for every new sample we have to collect or compute the distance. So let's say we have 1 million training samples in the corpus. For each testing sample we have to compute millions of times the distance matrix. So that is why it is important, and um, we have to use either feature selection method or the reduction method to reduce the number of features, redundant features, and we have to use some smart way of storing the data in the memory. So we'll talk about this in further in detail. So first is the parameter selection. In the parameter selection, the value of k is very important. How to decide what should be the value of k? So generally, the method is we try to find out the value of k using empirically. We see that what is the best value of k, which works best for our training data. And if the value of k is small, if you take this value of k is small, it will be very sensitive to the noise. So if you'll see an example in which let's say these samples. So if the value of k is small, let's say 1, so it will directly take the label which is very close to this. So it might be a noise for this sample and may not be, but it will be very sensitive to the noise points. And if we take the value of k too large, it will basically reduce the effect of the noise, but it will take the decision boundary very distinct. So I'll take one more example here. So if you'll see here in the first diagram that this sample, which is very in the red region. So this is a 3-class problem in which we have red region, blue region, and green region. If you notice this sample, which is in the red region, but because the value of k is very small, it will be treated as wrongly declassified. And if you'll see that decision boundary will also be very non-linear and very sensitive to the value of k. And if you'll notice here in the k is equal to 15, the red region, blue region, and the green region, you can notice that these boundaries are quite smooth, and which is quite better in the sense it is the effect of the noise will not be much, because these are the noise which makes misclassification for the small value of k. So this is important that uh, the value of k should be taken in a way that it should not be sensitive to the noise, and it should also be in a way that the decision boundary becomes distinct, at least distinct. Because when we'll take a large value of k and we'll increase this, so sometimes these classes will also overlap. So that is also important. And also it is important to see that if the training corpus is small, so if training data set is small, we have to take a small k. If for a small training set, if we take the value of the k large, so in that case, it is possible that the whole corpus will become within a value of k. So that will become 1k. And in that case, it is not possible. So if we have small training data set, we have to use small k. And when we have large training corpus, there is both the choices that we can have a small k or the large k, but that we have to decide based on the different possible values of the k. We empirically decide that, okay, what will be the value best suited for that particular data set. Okay, so the in general, what happens is when we use the value of k, so generally with small k, it is start with high error. If this is your error, so it will start with high error, and if we increase the value of k, it generally decreases the error, and after some point, it will either become very constant or it will move here and there in a particular range. So generally it happens in that sense. So the best value of k is when we have smallest error, And after that, the value of k, the error may be almost similar, but we choose the value of k which is uh, smallest, at the same time giving the minimum error. At this point of time positions, it is possibly there is a possibility of overfitting the data. So we choose the value of k, which is the optimal value of k. We'll also see with the hands-on demonstration of k nearest neighbor, and we'll see that what happens when we change the value of k in the performance. And next important thing is feature selection and scaling. As we have discussed, that it is possible that in the training data, all features are not important. We have to have remove the irrelevant features, because k-nearest neighbor is very sensitive for the irrelevant and noisy data. The reason is because the distance metric which we use generally take all the features as equally. It generally don't give importance to the more important features, and don't ignore the irrelevant or noisy features. So it is important to remove, otherwise the classifier may be biased and it will not perform good if we have irrelevant and um, noisy features. So that for that purpose, we should remove redundant and irrelevant feature using any feature selection algorithms that we possibly will talk in the different lectures and different sessions in this course. And once we have carefully chosen the features, the classification results with keenness neighbor can also be good. As we have already discussed, distance metric in k-nearest neighbor generally gives equal weightage to all the features, and hence scaling of all the features is very important in equal range and equal variance. Because if we don't bring the data, all the features in equal range, one feature may dominate. And for this example, if your person's height is in the range of 1.5 to 1.8, and the weight is in, let's say, 60 to 100, and some income is also there, one attribute in the range of 10 lakh, 10,000 to 2 lakh. So obviously the distance metric will give more weight automatically to the income feature. And that is not that we want to give to the classifier. So that is why scaling is very important. And there is other way of that giving the weights in the distance metric. If you have the importance, so in general k-nearest neighbor gives equal weights, but since if we already have the importance of the features, we can use weighted Euclidean distance. So if you can see, if you see this example, or sorry, this formula, in which this is a standard way of computing the differences between the different feature values. So wi, you can give the weights to each feature. So if, let's say, we have 5 features, so each feature we can give a weight. So let's say this is 0.9 or 0.6 and so on. So in this, if we can compute the, or we can have some way of giving the weights to the features, we can also use the weighted Euclidean distance metric. So we can give large weights which for the features which is important, and small weights to the feature which is less important, and we can remove or give the 0 weights to the features which are not important. Okay, so this way we can give the weights to the features, and automatically we can decide that which features will be important. Generally, there are 2 ways to decide the importance of the feature. One is we can use external knowledge with other feature important methods like information gain and so on. We can use feature weights, importance of the features, and use in this formula. And also we can use the the information of the importance of the features based on the distance metric itself. So for example, if a feature, let's say this is an example in which this is a testing sample, and these 3 are nearest neighbors. So we can also give weights to the samples, with more weights to the samples which is nearer. So for example, this sample is nearer, so we can give more weight to this label, this label, and less distance to this label, and less weight to this sample. So based on the reverse of the square of the distance, we can itself use as a weight to the samples. So that is also we call it as a distance weighted nearest neighbor algorithm, in which we can assign the weights to the neighbors based on the distance from the query point or the testing point. So the samples which are close will be more important, and the samples which are nearer but far compared to other neighbors will be less important. So we can use different methods uh, for giving the weights to the different neighbors. So if we have let's say 5 nearest neighbors, so all these 5 neighbors can be weighted differently. So based on the distance of a sample with the query sample or the testing sample, the sample which is nearer may be treated more importantly. So that is the idea, and that is called as a distance weighted nearest neighbor algorithm. And how we can work with this distance weighted nearest neighbor algorithm. For example, if we have 3 nearest points, so all these are the features, and these are 2 uh, classes, apple and orange. So for example, the sorry, the distance of the query sample with the first point is 0.38, and the distance of the second point from the test point is 0.51, and so on. So we can use the square of the distance and inverse of the square of the distance, and we can use these weights and then calculate. So for this apple class, we have total 15.96, and for orange we have total 3.84, and it means that weighted votes suggest that the prediction is apple. So instead of taking a simple majority giving equal weight to all the samples in distance weighted nearest neighbor, we generally give weights to the different samples differently. And there is other problem which we already discussed in another way in the previous discussions also, the curse of the dimensionality, because of all the samples are treated equal distance. So in high dimensional features, we generally have to remove the features which are not important, and because it can distort the performance of the model. And also it will give a problem that it is very difficult to um, compute the distance for large number of training samples. So in that case, we have to be careful, and we should remove the features which are not important in samples which are redundant. So that is a problem of the complexity. In terms of complexity, if the training corpus is too much very high, so generally we use fast data structures like KD trees to store the training corpus that is efficient in the terms of computing the distance metrics. And also we should remove the redundant features. It will also increase the storage requirement, and ultimately we have to use either fast data structures like KD trees to store, if they store the data if the training corpus is very high, or we should remove the redundant data somehow by doing the condensing method, in which we remove the features which are the samples which are redundant. Okay, so that's it from for the k-nearest neighbor algorithm. Now I will um, demonstrate you about how we can implement it in Python. If you have any doubt or questions related to k-nearest neighbor, please feel free to ask. Otherwise, I will demonstrate the code, how we can implement in different settings, how we can choose the value of k, how we can implement weighted k nearest neighbor algorithm. Please feel free to ask the questions if you have about the k nearest neighbor.